we'll take some simple examples on trusses now. That's it. Next we'll take up beams. So derive an expression for stress in any plane stress element. Let us derive an expression for stress, because ultimately in the problem we have to determine the stresses in the elements. So after determining the displacements, we have to determine the stresses in various elements. Then once you know the stress, force also you can determine. Just multiply by area of that element will get the force. Stress into area will give you force. So if you determine the stress, automatically forces will be known in all the elements. So how to get an expression for stress? So we know, it's a very simple example, that's all. We know strain in plane truss element epsilon is given by 1 by L. That expression you have to remember, I told. Just now I derived. It is minus L, minus M, L, M in global coordinates. U1, V1, U2, V2. Nodal displacement. That I have derived, B matrix. So epsilon is B matrix into nodal displacement. Nodal displacement we have to derive in regular problem. But once you derive the displacements, then you can find the stresses in each element. For each element, you know the direction to sense. L and L. L equals cos theta, M is sin theta for each element. You know the length of each element. So multiply by the nodal displacement. You will get strain. Then stress. Therefore, stress sigma is nothing but d E divided by L into or I will expand this because this is 1 by 4, this is 4 by 1, you get 1 by 1. That is stress. E by L sigma, that is 1 by 1. Stress in that element, only one element, one value. So this is E by L into minus L U1 minus M U1 Lu2 plus M. This is the expression for stress in any plane. After getting the n displacements, you can find the stress in that element by just knowing the n displacements and multiplying those n displacements by the respective direction cosines. Then E by L automatically by E by L you will get the stress. That is about that. Very simple step. Similarly, if you want to determine the forces, if you have to find the forces in all the stress members, so first you have to solve for displacement in the global coordinates, then you have to find the forces. Forces are nothing but the end force in any stress element is equal to A into sigma. Area sigma is stress into area of cross section. That area of cross section you know. That is that. So that is therefore force in any element is given by AE by L into minus LV1 minus LV1 plus LV2. Okay? That's all. Force or stress. This is the last step in the analysis, that is seventh step. You have to evaluate stresses and forces. Forces, only stress is the main thing. And once you know stress, it is only multiplied by area of cross. This is all. Then let us take pre-strain. Next example. Determine the load vector, because I have derived the element equation KE, that is element equation I have derived is difference matrix KE into Q is equal to P. This is the element equation. If you take this KE, you convert it into global coordinates, the K into global displacement, Q. Here you saw, these are all the global displacement. Element displacement is just Q1, Q2. If you take Q1, Q2 and KE, then this is the load vector. And in the global direction, KQ is equal to force vector. Now, I will determine the load vector. This right hand side, how to determine. I told you how to determine this K. How to determine this load vector? Given load vector, it is always in global coordinates. Given load will be always in the global direction. And of course, using these two, this is now, this also you can determine. I have given the expression now. Only unknown is this, that you can solve for the structure. Then once you know all those displacements, you can find the stresses or forces. That's the final step. Now in the element properties, we have to determine mainly this K. So here, as well as the load vector, F also we have to determine. F, if it is given directly, no problem. Usually, all the nodes should be only in the nodes. And nodes in the global direction. That's always known. So by taking the load direction, always we take the load acting in the upper direction positive. So we can say determine the load vector due to pre-strain load vector due to pre-strain on account of temperature change. Temperature change. Delta T. Temperature change. Delta T. Or it may be due to lack of fit. So while fabricating, some elements of the truss may be too short or maybe too long. So that gap, whatever is there, short gap or longer gap means you have to force into. Shorter gap means you have to pull it again and then weld it into the position, place in the position. That is also pre-strain. It is called pre-strain. If it is too short or too long, that's called lack of fit. There is a deficiency in fitting the member in position. Or it may be temperature change. There may be temperature variation, increase in temperature or decrease in temperature. In such cases, there will be expansion of the members. Due to that, some pre-strain will develop. And because of that, how to find the corresponding load vector. Otherwise, regular load, if it is given, that is known. Other than that load, due to pre-strain, temperature change and lack of fit, how to take it? Then we have to add all this, lack of fit, temperature, given external load. All the three are body force, surface force. Surface force is not coming into picture at all in trusses because stress members are not subjected to member loading. So only joint load. So joint load, always you take upwards, positive, downward, negative. That you have to remember while solving the problem on displacements. So now we will give the expression for the temperature change. So the pre-strain due to external load at joints and temperature change. Temperature change is given by epsilon is equal to BQ. BQ is due to the given loadings, given loading, BQ, or you can say pre-stress. The stress or the load due to external load at joints and temperature change, the load vector due to external load at joints and temperature change is given by, and straight away take that P vector, right hand side. Right hand side is that element equation K Q is equal to P. The P is given by A E into BQ minus P, or let's say equals E element, each element equals minus pre-strain into I will do like this. First, one by one, is given by the following. Is given by the following expressions. So, pre-strain due to a change in temperature of delta T with coefficient of linear expansion alpha 12 degrees centigrade is equal to alpha into delta. This is the strain. So this is the temperature change. Say from some value, whatever maximum temperature is there for which design has been done. Say there is a change in temperature, say by 50 degrees. The coefficient of expansion is known. If you multiply that, you will get that coefficient of the expansion with the change in temperature, you will get the strain. Therefore, stress due to temperature change is equal to stress is E into strain, E alpha delta T, and force due to temperature change force or load. Force or load due to temperature change is given by this A. Stress multiplied by the area of delta. This is that expression, force due to the temperature change at any one node. And you have to take care of that. Therefore, if it is a particular expression, therefore, load vector P due to temperature change is given by load vector due to temperature change Pt is given by AE alpha delta T into U1, U1, U2, so you have to multiply by this, by the corresponding U1, V1, U2, V2, that is that. Not that U1, V1, it is, minus L in global coordinates. This is along in one direction. Temperature change is in one direction. Along the member nodal points, you have to multiply this by minus L, minus L, L. This corresponding to the nodal node vectors in global coordinates. So that is, if you take it here, this element, then there is a change in the temperature delta T. Alpha is the coefficient of linear expansion, A, E, axial liquidity, length L. There is a sudden change in the temperature here. Then due to that change, what are the loads which are there at the ends in the nodal direction? Of course, the external loads will be there. That we have to add it to this temperature load. This temperature load is given by this. So this value multiplied by the corresponding L, M, this is the load here, corresponding this direction. In this direction, it is multiplied by minus L. In this direction, multiplied by minus L. In this direction, it is L into this much. In this direction, it is M into this much. So these are the temperature loads at the nodal points. Similarly, free strike, lack of fit. Lack of fit, suppose it is member, it is sharp by certain amount, delta, what they will give, value, delta. That delta divided by the length of the member, that is the strain. This is the extra length to be pulled or pushed into the position. So that divided by length will be the strain. So strain, then strain is no, instead of alpha delta T, it is that lack of fit value multiplied by, divided by length. That is the strain, free strain, due to lack of fit. Stress will be E multiplied by that. Then force will be A multiplied by that. And again, multiplied by direction cosine. That will be the corresponding loads at the equivalent loads at the nodal points. This is how you have to work out. If they give a temperature change in any member or all the members, if they give it, then you have to calculate the equivalent nodal loads. That's what I have told here. determination of load vector, that right hand side, u1 corresponding to u1 direction, v1 direction, u2 direction, v2 direction. What is the load? P direction, pu1, pu2, pv1, pu2, pv2 direction. What are the loads? Due to temperature change as well as lack of heat. That is due to tree strength, lack of heat or temperature change. How to find the equivalent load other than external load? So that external load will change, you load due to temperature change, load due to lack of heat, load due to self-weight, as well as any other load. Surface load is not coming. That we will take up in beam problem. That is right hand side load vector. Stiffness matrix is known. Right hand side the load vector is known. Only unknown is that Q. Kq is equal to P. That's the element equation. That Q into some displacement. Then once you know the displacement, stresses and forces, you can find it. This is the complete analysis of any problem. Now we will take up one simple example and close this truss analysis. This much information you should know before analyzing any truss. How to derive the equation for stiffness matrix, how to take care of secondary pre-strain effects. All this. And given load, of course, only thing you have to remember is if the loads are acting at the joints in the vertical direction, vertically up, you have to take positive. If it is given downward, you have to take negatives. So, say, analyze the truss shown in figure by finite element math. The same problem, I think we have worked in classical method, by classical approach. So now we can work by this finite element approach. We can work and compare the values. Take this load. So I will take a good example. The load is 50 kilonewtons, 500 millimeter square, and 50 kilonewtons. Given a plane truss, 1, 2, 3, 4, subjected to a load, P inclined to P at the node 3, acting at an angle 30 degrees with the vertical. Analyze this stress. Area of cross section of each member 500 millimeter square, E is equal to 100 dpa, and of course load is 50 kilonewtons. The first step. So the given problem is a plane truss problem. This is a plane truss problem. So you select a global coordinate system. You call this as global x coordinate, global y coordinate. First you fix up the structure with respect to a coordinate system and calculate the coordinates of each nodal points. There are 4 nodal points and there are 4 elements. So there are 4 nodes and 4 elements. So these 1, 2, 3, 4 are the nodes, elements. You call this as first element, second element, and third element. This is fourth element. 1, 2. I can just all the elements. Only numbering of nodes should be such that minimum bandwidth criteria should be satisfied. Otherwise, that's not. And the global degrees of freedom, you can say here 1, here, or you call this as coordinate 1, degree of freedom 1, degree of freedom 2 at node 1, at node 2, it is 3, 4, at node 3, it is 5, 6, at node 4, horizontal displacement 7, vertical 8. So there are 8 degrees of freedom, 4 nodes, 4 elements, and there are 8 degrees of freedom with 2 degrees of freedom per node. Both are translations, no rotations, because each joint is pin joint. These are the information first put together, basic information. So how many elements, how many nodes, what is the total degrees of freedom, and out of these 8 degrees of freedom, some are restrained. Here you have a hinge support, here you have hinge support, here you have roller support. So here hinge support, no displacement is possible, both horizontal as well as vertical. So that is your Q1, Q2, likewise Q7, Q8, as well as Q4. There are 0. Only you have to determine displacement along 3, 5, and 6. This you have to identify first. So kinematic indeterminacy is 3. That is 3. Out of this 8 degrees of freedom, only 3 are unknown. The rest are all known. Correct? Huh? This is what you have to determine. The one which you have to determine unknown displacement, that we call it as the kinematic indeterminacy. Degrees of freedom means general displacements. Right? That you have to mark it, and out of that, what is that you have to determine? That's kinematic indeterminacy. That's only thing. So they are nothing but Q3, Q5, Q6. You have to determine only displacement along 3, displacement along 5, displacement along 6. Q3, Q5, Q6, which is equal to kinematic indeterminacy. Each joint you have two displacements. Totally there are 8 displacements, that is 8 degrees of freedom. Out of that, because of boundary conditions, some are restrained. Here 1, 2, 7, 8 and 4 are restrained. They are not possible because of boundary conditions in the way of 2 hindered support and roller support. Here and the rest are all, the rest of the degrees of freedom we have to determine during our analysis. So your vector Q for the entire structure is Q is equal to Q3, Q5, Q6. This is what first you have to identify. Because in all that equations, I have derived Q right from Q at any point, displacement at any point in any member is given by NQ. That Q is this in terms of nodal displacement. Similarly, P matrix, that's also in terms of nodal displacement Q. K matrix, nodal displacement. All are in terms of nodal displacement. That's why this is called a kinematic indeterminacy is the main thing, or displacement method of analysis. This will be. Now, second step. So you need not have to bother about your element stiffness matrix now. Straight away go for global coordinate system because I have derived the global coordinate. So before that, let us take member information. Member information. So member, you prepare a table. There are member 1, member 2, member 3, member 4. There are 4 members. Each member I is equal to 1 to 4. Then the length of the member. So here you can write the coordinates. Here 0, 0 with respect to this global coordinate system. 0, 0. Coordinate of 2 is 4, 0 because it is 4 meters. And coordinate of 3 it is 4, 3. Vertical 3, horizontal 4, and coordinate of 4, it is 0 x coordinate, y coordinate is 3. So I told length is given by, this is j end of the member, k end of the member. Each member has j end and k end. Of course, that you can identify in the member information. So you can say member information. You can say Jn, Kn, left hand and right hand. You can identify. So Jn for member 1, you can take 1, Kn has 3 or 2. Here for member 2, Jn, you can take it as 4, Kn, or 3, 4, or 4, 3 better, 4 and 3. And similarly, number 3, Jn, you can take it as 2, lower and upper and 3. Then 4, it is 1, 4. Then you can find length. Length is xk minus square root of xk minus xj whole square plus yk minus yj whole square. Length of any member is given by x coordinate of kn minus jn, x coordinate of jn whole square. Similarly, y coordinate of jn minus y coordinate of jn whole square. So for number 1, you know straight away 4 meters. So you can write that 4 meters straight away, but you can check. So xk of 2, xk of 2 is 4. Then xj of 2, 1, xj is 1. x1 is 0. 4 minus 0 whole square, that is 4 minus 0 whole square is 16. Similarly, yk minus yj is 0, yj is 0, 0 minus 0 whole square, it is 0 square. So 16 plus 0, that square root is 4. But this formula kn for which you have written the coordinate, because for this number also, is here for number 2, it is 4 meters, all I will write everything in, say this, I will take 400 millimeters, 300 millimeters. So instead of 4 meters, we will take that 400 millimeters and 300 millimeters. Because it is easy for calculation. 2, it is again 400 millimeters, and 3 member 300 millimeters. 4th member, it is square root of this plus this. Or by this formula, you can do it. It is 400 square plus 300 square, that square root, it is 500. These are the lengths. Then area of cross section is 500 millimeters square. This is all in millimeters. Area millimeters square. All are 500 millimeters square. Then we can find AE by N. Because we need that AE by value. So here E is equal to 100 GPa. 100 GPa, that is 100 into 10 to the power of 9 Newton per millimeter square. Correct? So this I can write it as a Newton per meter square. Or this I can write it as 100 into 10 cube Newton per millimeter square. Or not 100 Newton square, or this 100 kilonewton per millimeter square. Here you can take it as 100 kilonewton per millimeter square. The P is given in kilonewton. I will maintain kilonewton. All others are in millimeters. So E is equal to 100. A is equal to 500. Area of cross section of each element member is 500. So AE is equal to 500 into 100. Right? That is 5 into 10 to the power of 4 divided by length. So for member 1, AE by L is 500 into 100 divided by 500, that is 100. Similarly for member 2, 500, 100 by 100, 500, 100 by AE by L, that is 500 into 100 divided by 400. L is 400. 400 means this is 125, this is 125. 5. So this is 3, 4, 500, 100 by 300. 300 means 166.7. Then this is 100. That is you have A by F for each member. This is A is in millimeter square, kilonewton per millimeter square. This is kilonewton per millimeter. That's the unit. And now you can write the stiffness matrix, second step. Stiffness matrix. First step, take all the informations given, identify number of nodes, number of elements, identify degrees of freedom, then prepare member information, which is required for computing the stiffness matrix. Then you know that stiffness matrix in global coordinate, it is given by that equation, you know, A by L into L square, M square, and L square, LM, M square, and LM, M square, minus L square, minus LM, minus LM, minus M square, minus L square, minus LM, minus LM, minus M square, L square, LM, and LM, M square. And that also you have to determine better. You determine for each member in the table M, so that you can compute it easily. The member information, direction cosines also you can determine. This L is nothing but xk minus xk by L. M is nothing but yk minus yj by L. X coordinate of kn, x coordinate of jn, jn, I have written, x coordinate of kn, x coordinate of jn, that difference divided by length, that will be your direction cosine L, M. Otherwise, if interaction is given, cos theta, sin theta, either way you can determine, because this is easier coordinates. So for first one, first element, straight away I can write because it is horizontal one. So direction cosine N is equal to 1, M is 0. That you can cross check. 1, 0. So N you can cross check. xk means x2, xj means x1, x2 minus x1, x2 is 4, x1 is 0, 4 minus 0, 4. 4 divided by, that is 4 means 400, because this I have converted into millimeters, so this will be 400, that you can make change. 400 divided by 400, that is 1. Similarly, yk minus yk by L, yk minus yk means y2 minus y1, y2 minus y1, 0 minus 0, 0, that is 0. Here also, xk minus xj, that is 400. This is 400 minus 0 divided by 400, that is 1. That you have to see which is the 1. You have to be very, very careful here. It is 4, 3. So x3 minus x4. Formula is xk minus xj, so it is x4 by xk, x3 minus x4, x3 minus x4. It is 400 minus 0. That's why you have to be careful. Suppose if you take this as 4, 3, then it is 0 minus 400. Minus 400 you have to take, your direction cosine will be negative. That you have to be careful. That's why I changed here 4 3 now 3 4. So this is 400 minus 0. So it is again 1. This is 0. Or 3 3. 300 minus 300. It is 0. So this coordinates you change it. So it is, I change it for easy computation. Is 400. That's all. So then for 3, this member, 3 member, it is x3 minus x2. x3 minus x2. 400 minus 400. It is 0. So here, this is 0 and this is x3 minus, y3 minus y2. y3 minus y2. y3, that is 300 minus 0. 300 divided by 300. This is 1. For vertical member, it is 0, 1. Horizontal member, 1, 0. For inclined member, you have to work out. For this inclined member, it is 1, 4. So that is x4 minus x1. x4 minus x1. 400 minus 0, 400 divided by 500, that is 0.8. Then 300 minus 0, 300 by 500, it is 160. This also carries. Then substitute those values here. For each member, you can find K1 is equal to AE by L, it is 125 into L square, it is 1, LM 0, then LM 0, M squared 0. So then this is minus 1, 0, 0, 0. Then this is minus 1, 0, 0, 0, 1, 0, 0, 0. This is stiffness matrix of member 1. So you write the degrees of freedom. 1, 2, 3, 4. 1, 2, 3. Here, unknown displacements correspond to 3, 5, 6 that you have to calculate. This is 1, 2, 3, 4. Here also 1, 2, 3, 4. Then you find K2 for member 2. K2, this is K1. For member 2, AE by L is 125. That is same thing. Same matrix, because it is 1, 0 only. You can write simply 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0. The coordinates are for member 2, it is 7. Now first you have to take which is Jn. 4 is Jn. This is Kn. So this is 7, 8, 5, 6. While writing the degrees of freedom, first Jn degree of freedom, then Jn. That also you have to be very, very careful while writing it. These are the things. Otherwise, it will mix up and things will go. You have to be carefully write all these things. It is 5, 6, here also 7, 8, 5, 6. Write it down. Then you write 3. So in computer, automatically it will do correctly. You are identifying I, J, I flow, J column, and there also Jn, first one, second one. It will automatically read. While doing hand computation, you have to be careful and take the appropriate value. Then K3, it is this vertical member for which AE by L is 166.7. for this L and M are 0 and 1. So L squared is 0, M squared, Lm is 0, this Lm 0, M squared is 1. So this will be minus 1. Here 0, 0, 0, minus 1. Here it is 4, 1. So now you have to which of the degrees of freedom? Here for 3, 2, 3, 2 to 3, it is 3, 4, 5, 6. Carefully you have to write the degrees of freedom. 3, 4, 5, 6. You have to write. Then last member, the stiffness matrix is given by K4. It is AE by L. 100 into L square, it is 0.64, Ln 0.6 into 0.8, 0.48, this is 0.48, M square is 0.36. First 4 elements, write it, change its sign, that is this, minus 0.48, minus 0.48, minus 0.36. Here also same thing you write, minus 0.64, minus 0.48, minus 0.48, minus 0.36. Here same as this, 0.64, 0.48, 0.48, 0.36. This is the stiffness matrix of fourth element, for which the degrees of freedom, n j is 1, k n is 4, 1 to 4. So this is 1, 2, 5, 6. Like that you have to number 1, 2, 5, 6. Then for the entire structure, you can write all this, you can plug and write for 1, 2, 3, 4, 5, 6, 7, 8, assemble. But if they ask in the problem, find the global stiffness matrix for the truss. If they ask that, you assemble all these and write that same matrix, which is the global one, that is 1, 2, 3, 4, 5, 6, 7, 8. That entire thing. Each element values, you have to read it and enter it. Some are common and you have to add that 5, 5, 5, 5. You have to add it and write in that. That is the global stiffness matrix. Sometimes they will ask only just find the global stiffness matrix or assemble global stiffness matrix. That you have to assemble. Then after assembling it, you have to take out only the elements of the stiffness matrix which are required for these determination of these unknowns. That is corresponding to 3, 5, 6 only. That is called reduced stiffness matrix. Reduced stiffness matrix. That we call it as KD. That is stiffness matrix corresponding to unknown displacements. Unknown displacements. So that is nothing but you have to find out corresponding to these 3, 5, 6. 3, 5, 6. So that means 3, 3. 1, 2. First element 3, 3. You have 3, 3 here. That is 125 into 1. 125. Then here you don't have 3. Here you have 3. 3, 3. 0. And here you don't have. Correct? So it is only 125. Is it clear? I will take that also inside now. Next, 3, 5. How to find 3, 5 from element 1? No, you don't have. Here, no. Here, 3, 5, 0. 1, 6 is, that is 0. Then 3, 6. Here, 3, 6, 0, 3, 4. Okay, we say 3, 4. No, 6.
4.
It is 4. Nothing. Then here, no 3, 6. Here, 3, 6, 0. You see? That's why I told you most of the elements will be 0. That's why bandwidth, half bandwidth has to be minimum. I was telling. This difference matters for computation purpose, for storing the code space. Next, this is symmetric matrix. This will be 0, 0. Here also you can observe the global, each of these are symmetric. Here also global also symmetric. This also should be symmetric. So whatever is there, you can find. Next you can find 5, 5. 5, 5 you don't have. 5, 5, 1 into 125. That 125, of course, same. 1 into 125. Then 5, 5, 0 is only 125. Next, 5, 6. This rule fully you have to do it. Reduced thickness matters corresponding to this kinematic independence. So then 5, 6, now 5, 6, 5, 6, 0, 5, 6, 0. Likewise, 6, 3, you don't have. 6, 3, you don't have. 6, 3, it is again 0.
6, 5.
Then, 6, 5, 6, 5 we have to see. Here, no. Here, 0. Yeah, here also 0. Okay, fine. 0. Because it has to be symmetric. That also is a check. Okay? Lastly, 6, 6. No. 6, 6, 0. Here it is 1 into 166.7. Oh, this I didn't take at all. I didn't consider this at all. Here, of course, 3 is not there. 5 is here. So 5, 5. Here you don't have. Here 5, 5 is 125. Here 5, 5 is there. 0.64 into 100. That is 64. 64, I have to add it. 189. 5, 5 is not the best. 125, it is 189. I was wondering. Then 5, 6. 5, 6 is not here. 5, 6 is 0 here. 5, 6 is 0. Here you have 5, 8. 0.48 into 100. 48. 5, 6 is 48. Then this has to be 48. Then 6, 6. Don't have 6, 6, 0. It is 166.7. 166.7 and 6, 6. 0.36 into 100. 36. So this will be 202.7. 202.7. So this is the reduced stiffness matrix. So this much information is there. Then last thing you have to find there are no displacement from this. That's all. So next step. So we have the element equation in this total structure. Element equations KD into unknown displacement Q is equal to ED. PD you have to find out. KD I have determined. Load vector you have to find out. Load load vector corresponding to this one only. So load vector, that also I will show you here. This is where you have to add that temperature effect and as well as lack of it. That's all the change. This is same you have to do. Then load vector. This you have, we have. This is the equation. Structure equation, global structure equation, global unknown stiffness matrix, unknown displacements. This. So load vector, that you have to compute. Load vector, you don't have temperature things given, you don't have lack of it, only the given load. So for given loads, you can take it in kilonewtons. So this is at 30 degrees. So you can resolve this in vertically down and this way. Right? Load is acting like this. So you will get a downward load and a load from right to left. So this will be P, this is P sin 30. P sin 30, this will be P cos 30. Because this is 30 degrees, this component will be adjacent cos. This component opposite to the theta sin component. That you remember. Always, wherever you have theta, opposite to that theta and that side, that is sin. Adjacent side to theta is cos. So this is adjacent, that is this cos theta. This is opposite sin theta. So P sin 30, P cos 30, that is 50 sin 30, 50 cos 30. You can find out that will be corresponding to degrees of freedom 5 and 6. Right? Your load vector P is equal to, for total entire structure, P is equal to load vectors corresponding to 1, 2, 3, 4, 5, 6, 7, 8. For all the degrees of freedom. For 1, it is 0. For 2, no load is given. Otherwise, if there is suppose settlement or temperature effect due to that, if it is coming, that load you have to take. EA alpha T, I told you to compute, and that value corresponding to the degrees of freedom, you have to write. And 3, no load. 4 also no load. 5, it is P corresponding to 5 minus P sin 30. Correct? Minus P, because it is from right to left. We have taken the degrees of freedom from left to right positive. This is opposite. Then 6, it is P cos 30, that's again P cos 30. P is 50, you can substitute. Or if you have taken newtons, convert 50 to newtons, that's all. 78, no load. So this is how you have to prepare the load vector. Stiffness matrix, load vector. Here you have to take PD corresponding to unknown displacements 3, 5, 6. That is reduced load vector. This is total load vector, total load stiffness matrix, similar to that, total load vector, then reduced load vector, vector PD is equal to corresponding to only 3, 5, 6. 3, it is 0, corresponds to 5, it is minus 3 sin 30, corresponding to 6, minus 3 cos 30. Now PD is known, KD is known, KD you have found out. Only a known Q, which is nothing but Q3, Q5, Q6. So Q3, Q5, Q6 is nothing but KD inverse into PD. You will get unknown displacements. So when unknown displacements are known, all other displacements are 0. You can find these stresses in it. I have given the formula minus m for each element. For each element, we have the degrees of freedom. So you can multiply and find the stresses as another. Here, due to temperature change, lack of it, you can introduce. Is it clear now? This much information is there. Analysis means only this. First, we have to find out kinematic indeterminacy. That we have to find out after developing all the entire structure stiffness matrix from that reduced stiffness. Similarly, all known vectors reduced load vector. Then take only that reduced load vector, reduced stiffness matrix, find their known displacement. And once displacement is known, all other displacements are zero. You take each member separately, find the stresses. I have given the formula, develop find the stresses in each member or forces, each member is different. So this is the complete analysis of plane truss. I have developed the equation for stiffnesses and I have given the procedure for computing load vectors due to temperature change, lack of it, that is pre-strain, whenever it is given, and how to develop the structure stiffness matrix, then from that how to take reduced stiffness matrix, reduced load vector. So here either you can invert the stiffness matrix or you can take equations, three simultaneous equations in these three unknowns. You can solve that equation. Either you can solve the equation or you can invert the matrix and multiply by the TD vector. You will get unknowns. So this much information is there in the analysis of truss. So next class, last class, I will tell you how to solve beam problem. Like this itself. You have to develop stiffness matrix for the beam element. You have to find the load vector for the beam. There member beam load is also there. How to find the equivalent joint load, all those things I will tell. Then how to find the unknown displacements there also. And how to find the internal member forces shear. That we will take up in the last class. I think.